Now, let us consider the relationship between convex function and convex set. Two important concepts often used in establishing the relationship existing between the convex function and the convex set are: 1. The epigraph of a function, and 2. the hypograph of a function. First, let us look at the epigraph of a function. The epigraph of a function f is the set of all points on or above the curve y equal to f of x. That is, the set E of all ordered pairs xy such that y is greater than or equal to f of x is the epigraph of f. We use this to illustrate the epigraph of a function. This is the function f of x. That's y equal to f of x. And this is the epigraph E. You can see the set of all points, that is the portion shaded blue, colored blue. The set of all points here are on or above this curve. So the above diagram shows that the epigraph of a convex function is a convex set. Clearly, this set E is a convex set, because if you pick any 2 points here, the line segment joining the 2 points will still be within the set. So the epigraph of a convex function is a convex set. Now let us look at this other one. This is our y equal to f of x. Then the set of all points on or above this function is this. Note that our function here, y equals to f of x, is a concave function. So the set of all points on the curve or above the curve is this set. Clearly, as you can see, this set is non-convex. You see, the above diagram shows that the epigraph of a concave function is a non-convex set. You can see the portion colored green is non-convex, because it is possible that if we pick 1 point here and 1 point here, the line segment joining the 2 points will not fall entirely in E. So that set E is non-convex. The epigraph of a concave function is a non-convex set. Okay, now let us consider this function y equal to f of x. The function y equals to f of x is non-convex. Then what about its epigraph? That's the set of all points on the curve or above the curve is this shaded portion E. Clearly, this set is also non-convex, because you can pick a point here and another point here, then the line segment does not lie entirely in E. So the set is a non-convex set. So we say that the above diagram shows that the epigraph of a non-convex function is a non-convex set. Now, let us look at the hypograph of a function. The hypograph of a function y equal to f of x is the set of points on or below the curve y equal to f of x. That is, the set H of all ordered pairs xy such that y is less than or equal to f of x is defined to be the hypograph of a function f. We illustrate this using diagram. We consider the concave function y equal to f of x. This function is concave, and this is the set of points, that's the region colored blue, is the set of points on this curve or below. As you can see, this set is convex. So the above diagram shows that the hypograph of a concave function is a convex set. Now we look at this other illustration. We are considering the hypograph of a convex function. The function y equal to f of x, that's this curve, is a convex function, and this is its hypograph, the set of points on the curve or below the curve. This is the hypograph, and clearly this shaded portion is a non-convex set. So the above diagram shows that the hypograph of a convex function is a non-convex set. Let us take on this lemma 1. If the function f is convex over a convex set S, then for any real number lambda, the set A defined as the set of all x such that x is element of S and f of x is less than or equal to lambda is convex. Let us illustrate this using this diagram. This curve y equal to f of x is a convex function defined over a convex set S. That's this red line is a convex set. Now let us pick lambda here so that we consider the set of all points x such that x is element of S and f of x is less than or equals to lambda. So if we take this line to be the line f of x equal to lambda, then the set of all points on f below this line is from here down here. You can see that all the points on this curve are below this line. So the set of all points in S such that that f of x is less than or equals to lambda is the set of points from here to here. So the set colored yellow here is our set A. You can see all the points in this set A belongs to S, belongs to the real line S, and f of x is less than or equal to lambda. And clearly this set A is a convex set. Please note, if the function f is non-convex over S, then A is not a convex set. Let us illustrate this with this diagram. Okay, you can see this curve y equals to f of x is non-convex, and this is the line f of x equals to lambda. This function f of x is defined over the real line label S. Then the set of all points on the curve which are below this line, the dotted green line. You see this portion of the curve is below this line. This portion is above the line, while this portion is below the line. We are interested in those portions that are below the line. That is this portion and this portion. So you can see the set of all points x which are element of S such that f of x is less than or equals to lambda is from here to here and from here to here. So if we label this first set as S1 and this second set as S2, you can see that our set A, which is defined as the set of all x such that x is element of S and f of x is less than or equals to lambda, is S1 union S2. And clearly, since S1 and S2, you can see S1 and S2 here, they are disjoint set. This set A can never be a convex set, because if you pick a point here and pick another point here, the line segment joining the 2 points would not lie completely in A, since part of it will belong to this portion which is not in A. Hence, the set A is a non-convex set. Theorem 2. If a function f is differentiable, then f is convex over a convex set S. If and only if, for all point xy element of S, f of y is greater than or equal to f of x plus y minus x transpose times the gradient of f of x. Example 2. Consider the function f of x1 x2 equals to x1 squared plus x2 squared, which is convex over R2. Show that f of y is greater than or equal to f of x plus 1 minus x transpose times the gradient of f of x. Solution. Let us take the point x to be x1 x2 transpose and y be y1 y2 transpose. Then the gradient of f, that's differentiating the function f of x equals to x1 squared plus x2 squared. Differentiating with respect to x1 will give us 2x1. Differentiating with respect to x2 will give us 2x2. Then f of x plus y minus x transpose times the gradient of f of x is equal to, please, f of x is, remember, is x1 squared plus x2 squared plus y1 minus x1 y2 minus x2 times the slope. This is equal to x1 squared plus x2 squared plus, when you multiply this vector by this will give us 2x1 y1 minus 2x1 squared plus 2x2 y2 minus 2x2 squared. And this is equal to minus x1 squared, that's x1 squared minus 2x1 squared will give us minus x1 squared. X2 squared minus 2x2 squared will give us minus x2 squared plus 2x1 y1 plus 2x2 y2. Rearranging the last equation, this will give us minus into x1 squared minus 2y1 x1 minus into x2 squared minus 2y2 x2. Let us now complete the squares here and here. So completing the squares, this will give us minus into x1 minus y1 all squared minus y1 squared. Remember, when you divide the coefficient of x1 here by 2, that will give us minus y1. You square it, add and subtract. So that will give us the expression inside this bracket here. Then minus the same thing here. This will be x2 minus y2 all squared minus y2 squared. And this will give us minus into x1 minus y1 squared minus into x2 minus y2 squared. Please, this minus y1 squared will become plus y1 squared. Minus y2 squared will give us plus y2 squared. Clearly, what you have here, this is a negative quantity. This is a negative quantity. So we are adding it to these two terms. Okay. So this term plus this term minus this clearly will be less than or equal to y1 squared plus y2 squared. But y1 squared plus y2 squared is f of y. So what we have shown here is that f of y is greater than or equal to f of x plus y minus x transpose times the gradient of f of x.